Hello, welcome back. Chapter 5, Video 2. Linus Pauli and his quantum numbers. Now, Pauli won a Nobel Prize for his description of what he said was the locate an electron. His description of the location was based upon 4 properties. If you knew these 4 properties, each electron in an atom has its own unique set of those 4 properties. And what it means is that no 2 electrons can share the same area of space unless they are spinning in opposite directions. So we're going to get to that in just a moment. So the importance of the Pauli numbers is knowing where the electrons are gives us an indication of how bonding will occur. There are 2 types of electrons. First, there's something called valence electrons. And valence electrons are high in energy. Oopsie poopsie. High in energy. Used for bonding. And are found outside what we call the core. We're going to call it noble gas core, and we'll talk about that in the next video. Found outside the noble gas core. And then there are things called core electrons, and sometimes called kernel electrons. And they are low in energy, which means that they are stable, whereas the high energy ones are unstable, and they are not used in bonding. And are found inside the noble gas core. Alright, so Pauli said there were 4 things you need to know to locate these electrons, whether they were valence or core electrons. He said the first thing you have to know is what he called the principal energy level number. And what he did was he took these 4 qualities and these 4 properties rather, and he translated them into a 4-digit code for each electron, sort of like a zip code. Like if you have 08852, that actually means something. 0 means New Jersey, 8 means Central New Jersey, the next 8 means Middlesex County, and then the 52 represents the Monmouth Junction post office. So what he said was this first number is the main number for locating an electron, what he called the quantum number, and that it referred to the main energy level that the electron was in. So the higher the number, the further away from the nucleus. So if you were in the 4th energy level, that electron is much further away than the 1st energy level. And we're going to get to a point where we're able to match this to the periodic table. I'm not going to do that right now. I'll do that in another video. The second property referred to the sublevel. And each of these sublevels have its own different shape and its own different code number. And that the sublevels are not equal in energy. The S shell is the lowest in energy. So if we let's write energy. If we go from low to high, the S sublevel is slightly lower in energy than the P, which is slightly lower in energy than the D, which is slightly lower in energy than the F sublevel. So he said the second property is what sublevel is that electron in? Now we're going to get into a little bit what's called overlap. Sometimes the sublevels overlap each other, and I will get to this at the end of the video. The third property, oh, by the way, the second number is called the azimuthal number. The third number is called the magnetic moment, and that refers to the orientation of that suborbital in space. In other words, with the P shell, there are three orbitals. There is the PX, the PY, and the PZ, and that represents, again, geometrically, which axis they're lying along. The px, of course, lies along the x-axis. Now, these 3 orbitals, what we call degenerate, which means equal in energy. So the S shell on the second number is lower in energy than the P shell, which is lower in energy than the D shell. But once you get to the orientations, the PX, the PY, and PZ all have the same amount of energy. The 5 different d orbitals all have the same amount of energy. They're all considered degenerate. And the fourth refers to the spin. There's only 2 directions an electron can spin in. And if one electron spins in the up direction, that means in order to be in the same orbital, the other electron has to spin in the down direction. So there are 2 electrons that fit each orbital. And again, Pauli came up with what was called the Pauli Exclusion Principle. Each electron has to have its own unique set of 4 quantum numbers. Okay, so how does that work? Well, we're going to come back to that. I'm going to show you what's called an energy orbital diagram for this. So let's copy this, and I'm going to ask you to copy it and put it in your notes as well. Okay, let's paste it. There we go. Let's put that in our notes. All right, so I'll pause and wait for you. All right, you're back. When we put electrons around the nucleus, they're negatively charged, so they're attracted to positively charged particles, the protons. So the electrons have a tendency to try to get as close to the nucleus as possible. And when they are close to the nucleus, they release energy. When they move away from the nucleus, they gain energy. We studied that in chapter 4 with the Bohr atom. So the way electrons configure themselves around the nucleus is based upon what we call the Aufbau Principle. Now, the Aufbau Principle, German word, means building up. It means you're going to fill in the low energy levels first before you fill in the high energy levels. Now, there are some exceptions to this that we're going to talk about in chapters 6 and 10, but for now, everything we give you is going to follow the Aufbau Principle. So if we had 1 electron in an atom, it's going to go right here. I'm going to put a number 1 over it in the 1s shell, because that's the lowest energy shell. Now, we said that each orbital can have 2 electrons. So the second electron also goes in the 1s shell, but has a down spin. When they have opposing spins, they still repel each other, but it reduces the repulsion enough to allow them to share the same area of space. All right, so where does the third electron go? Well, the third electron goes in the next lowest energy level that's available. Right here, in the 2s. And the fourth electron also goes in the 2s shell. Now, once you get to the 2p shell, now you have the px shell, the py, and the pz. So we put the 5th electron here in the px with an up spin. Now the question becomes, the 6th electron, should it pair up next to the 5th electron, or do you suppose it should spread out? And of course, electrons are all negatively charged. They should spread out. So the 6th electron goes into the py shell with the same spin. This is called parallel spinning electrons. So we're going to have parallel spin. And in advanced chem, we'll study that parallel spin actually creates magnetism. And then the 7th electron spreads out with a parallel spin into the PZ shell. So this idea for the 5th, 6th, and 7th electrons spreading out before they pair up is something called Huns Rule. And Huns Rule says that when electrons enter degenerate orbitals, orbitals that have the same energy, they try to spread out as far as possible before they pair up with opposing spins. So where does the 8th electron go? Glad you asked. Goes right here in the 2px. So the 8th, then the 9th goes in the 2py, and then 10 in the 2pz. And we can continue along doing the same thing. Here's the 11th, here's the 12th, 13th, 14th, 15th, in accordance to Huns Rule, right? Parallel spinning. And then the 16th, 17th, 18th. Now, once you get to the 3D shell, the 3D shell is actually higher in energy than the 4s, and this is created by something called the spin effect. Even though the 4s shell has more quantum energy, the 3D shell has more total energy. It has less quantum energy, hence the 3 in front of the D, 3D energy level, but because it has 10 electrons and they spin near each other, they create angular momentum. So the 3D electrons have angular momentum that the 4s do not. Now, do you have to know that at that level? At this level, no. You just have to know that the 4s shell actually gets filled up before the 3D. So we're going to put the 19th here and the 20th, and then 21, 22, 23, 24, 25, spread out into the D shell according to Huns Rule. Okay. So how do you figure out the 4 quantum numbers then for an electron? Well, the first thing you have to do is locate the electron. Let's say, for instance, they want us to come up with the 4 quantum numbers for, I don't know, let's do this 14th electron right here. Do a darker color. 14th electron. Well, what do I know about the 14th electron? Well, I know that the 14th electron is found in the 3p shell. So instead of writing 3p, the code number for p is 1. We're going to go over those code numbers in a moment. So 31 stands for 3p. And then the way they do degenerate orbitals, I'm going to erase this so it's not so cluttered. That we can get rid of all of this. Right? The way they do degenerate orbitals is sort of like a number line. They assign the middle orbital the value 0, and then the number line becomes more negative to the left and more positive to the right. So let's say we're looking at the 3D orbitals and we want to come up with the 3rd quantum number. The way we do that is we assign the middle orbital 0, and then these become more negative as you go to the left and more positive as you go to the right. So back to our 14th electron right there. It's in the 3p shell. It's in the middle orbital, the pxy. So we're going to put a 0 there. And now with the spins, if it's an up spin, they're going to use the term positive 1/2. And if it's a down spin, then they're going to use the term negative 1/2. So this is an up spin. So we're going to do positive 1/2. So the numbers are 310, positive 1/2. The 31 stands for 3p. The 0 stands for the middle orbital, which is the py. And then the positive 1/2 stands for the up spin. All right, let's try a different one. All right, what are the 4 quantum numbers for, I don't know, let's do 21st electron. 21st electron in any atom. So first thing I have to do is locate it. So I'm going to fill in my diagram. 1, 2, 3, 4, 5, 6, 7, according to Huns Rule. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Here's my 21st electron right here. Number 21 is in the 3D shell. All right, the code number for 3D is 32. Now, which orientation is it? This is the middle one. So this one becomes -1. This one becomes -2. It's in the -2 orientation. And it's an upspin. So we're going to use positive 1/2 as the value. And we get 3, 2, -2, positive 1/2. We're going to come back to that in just a moment. All right, so back to our little notes. All right, the 4 quantum numbers. First number is the energy level. The second is the sublevel or azimuthal number. The third is the orientation in space, which is called the magnetic moment number. And then the last one is the spin number, up spin or down spin. So here we go. Whatever energy level that you're in, that's the number you use. So if the electron is in the 3s shell, you use 3. If the electron is in the 4d shell, you use 4. Now the sublevels have code numbers: 0 for S, 1 for P, 2 for D, 3 for F. The third number, we said you find the middle orbital. Now the S shell only has one orbital, so the S shell always, the third number equals 0. But you find the middle orbital, assign it a value of 0, and then to the left they become more negative, and to the right the numbers become more positive, depending upon where the electron is. And then lastly, the spin number, either positive 1/2 for an upspin or negative 1/2 for a downspin. So first, second, and third electrons. Let's go back to our chart. Where's the first electron? Right here. First electron. So the first electron in any atom is in the 1s shell. So we're going to write 1, 0. And then it's in the middle orbital because there is only one orbital. So that's a 0. And it's an upspin, positive 1/2. The second electron, located right there. So the 4 quantum numbers are, well, the second electron is in the 1s, so we write 1, 0. And then it's the middle orbital. S shells always have a third number equal to 0. And then it's the downspin, so we write negative 1/2. All right, let's try one more just to make sure that we have it. All right, what are the 4 quantum numbers? 4. I don't know, let's make something up. How about the 17th electron in any atom? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, according to Huns Rule. Again, 13, 14, 15. And then we come back and pair up. 16, 17. So there we go. There's our electron, number 17. And 17 is in the 3p shell. So we're going to write 3, 1. And it's in the middle orbital, so we're going to write 0 for the orientation. And it's a downspin, negative 1/2. Now, do understand, this isn't a very intuitive way of doing things. But it is the first way that came out, and there is some people who still use it. Most college professors, however, do not use it anymore, but it's still taught. Let's see if there's anything else I need to add about the 4 quantum numbers. Huns Rule we talked about. We talked about degenerate orbitals, parallel spinning electrons versus paired electrons. And in the next video, I'm going to do basic electron configurations, which is a better way of describing where the electrons are. But there was something I think I forgot. Oh, how is this related to the periodic table? All right. That was right here on the first slide about the quantum numbers. So how is it related to the periodic table? Well, the energy levels are the row numbers. So let's go back and find a periodic table here. It's been quite a while since I put one on the slideshows. Oh my goodness. It's really been that long since I posted a periodic table? It's making my head hurt. It's a waste of time and footage. There's a teacher, there's nomenclature. Here's a periodic table. Okay. Let's do that. And let's go back through and erase some of these off of here. The way the periodic table is designed is it shows you where the outermost electron is in terms of the orbitals. In other words, the electrons in the first and second row are what we call S-block electrons, which means their outermost electron is in the S shell. If the element is in row 1, then the outermost electron is in the S1 shell. If it's in row 2, then the outermost electron is what we call an S2 electron. Still in the S shell, but it's the second electron in the S shell. When we're dealing with rows 3 through 12, these are called the D block elements. Again, their outermost electron is found in a D shell. So in the third row it's D1 all the way over to 12, where the outermost electron would be the 10th electron in the D shell. And then for the elements over here, this is called the P block, and down here this is called the F block. Again, for the same reasons, the outermost electron is found in that area. So here, group 13, the outermost electron is the first electron in the P shell, and 14, second electron in the P shell, 15, its outermost electron is the third electron in the P shell, etc. Now, the quantum number is based upon the row number. So here in the first row, we only have an S shell. So in the first row, we're dealing with the 1s orbital. In the second row, we have an S block, but we also have, come on man, don't do that. We also have elements in the P block. So in the second row, we have an S, and then we have a P. So in the third row, we have an S, we have a P. Now you're saying, well, where did the D block go? Well, remember, there's overlap. So the D block actually comes after the 4s, and you'll find it in the fourth row. So 3s, 3p, 3d. So, and then we get to the overlap, which we're going to talk about in detail in chapters 6 and 10. We're going to do a little bit with it here, and then we'll talk about the F block elements in chapter 6 and 10 as well. But for now, again, the row number is the quantum energy level. So fourth row, S shell, that means your electron is in a 4s. Fifth row, P shell, your electrons are in a 5p. And then we will deal with the D and the F block in another video. All right. Thank you very much.